Hello and good morning. Please, can you hear me?
Yes, sir. Good morning, sir.
Morning. Okay. I'm hoping the others will join very soon. But the first part is something we did last semester. So I hope by the time we get to the second part, they are here. Okay. So this is Unit 3. That deals with the various forms of differentiation method. So you differentiate a function and you get some sort of results. So last semester, when we look at differentiation in Unit 1, we saw some of these properties, but this is going to go a bit in detail, and the properties you see how we handle them. So we'll be looking at when we differentiate and we get what we call indeterminate form, a type of differentiation where you get numerator and denominator as 0 over 0 or infinity over infinity, or 0 times infinity, or infinity minus infinity, things like that. How do you handle them? And in doing that, we will have to revisit the L'Hopital rule. L'Hopital rule talks about to differentiate the function when after you substituted the limit function or limit value, and then the results are giving you indeterminate form. Then we apply L'Hopital rule. Then there are two theorems we'll be looking at. Both of them are very similar. One will take a specific value, the other will take a range of values. We call this the Rolle's theorem and the mean value theorem. Okay, so what I try to do is combine every topic in unit 3 into this. It's quite a lot, but yesterday I was trying to finish up and I was realizing it is a lot. So what I'm doing is I'm looking at session 1, session 2, session 3, session 4, and even questions on session 5. But I didn't add a PowerPoint on session 5. As for the session 6, they are virtually application. And each of these topics, I take one application or so. So I think session 6 it will be covered. So the PowerPoint we will be looking at will cover all this, okay? And the questions will cover all this. Okay, so please kindly take note of that as we go on. So we'll look at these topics in the PowerPoint, and then the applications will show. Then what I normally do, I have given you a worksheet. Now, I just went to the LMS a few minutes ago to check your whether you are accessing it. And last week, because it was supposed to be self-study, I uploaded 2 quizzes in there. And I realized that the first one, 7 people have attempted it. The 7 people who have attempted it, there are 7 here. And then the second one, 5 people have attempted it. The second one on the maxima and minima. Let's quiz on maxima and minima. That one too, you have 5 attempting it. Coincidentally, for today's lesson, I've already uploaded a quiz as well. So I will recommend that if you haven't tried your quizzes, please try and do them when you are less busy. Like I will pick the missing questions straight away from the quizzes already here. Each of these quizzes are over 100 questions. So in the midterm, we just pick a few from each one of them. Okay, so kindly take note. This one, somebody has attempted, is actually doing it right now. I don't know the brave student who is doing it, even though we haven't tackled the topic. But please, kudos to you. Keep on using the quizzes to be able to address your issues, especially the topics one after the other. Okay, so I think Kingsley is also on right now. So it's left with a few more. So let's begin. Like I said, the first part will take care of some of the things we saw in the last semester topic, especially the Unit 1 topic, differentiation. So the way I've done this is that I didn't put all the learning outcomes at the top. When I take the topic, then I bring the learning outcomes. So we are starting with indeterminate forms. So with this, we want to identify the 7 standard forms. Okay, there are 7 standards of them. As semester, we just pick 1 or 2, but here you see that there are more than just 1 or 2. So let's look at all the various forms of indeterminate forms. And then we distinguish between them, okay, from what we call undefined expressions. You know, sometimes when you are given a problem, I tell you that it gives you undefined. Undefined and indeterminate are a bit different. So we want to look at their differences. Now, then we'll look at the various methods in solving indeterminate. There is a factorization method, okay? There is a rationalization method, okay? And then there are also limits, standard limits, especially when you are dealing with trig functions. There are standard limits you will deal with. Now, and sometimes we may have to transform the product and the difference and exponential form in indeterminate form. So when you get a certain one of these standards, you may have to convert that standard into either a logarithm or exponential form so that you can be able to evaluate it. And then, like I said, for each one, I'll pick one application in reference to engineering so that we understand what these things does to functions and equations. So now let's review the knowledge of limit. Last semester we did limits. Now what is a limit? So limit is described as a value approaching by a function as a particular value of that x approaches a point. That's a concept of a limit. So our initial knowledge of limit is, first of all, attempt to do direct substitution. If it works, then you are good to go. But if it doesn't work, and then you may have to use the technique we are learning today. So when you do the direct substitution, a final value gives you the limit when the substitution is valid. But when the substitution gives you invalid, or it gives you answers that are not valid, then we are going to now use the indeterminate form to be able to do further analysis. So that is the review of limits. Limits, just substitute the limiting function. If the answer is okay, you go on. If it is not okay, then we will approach the question using the various techniques in indeterminate form. So the indeterminate form, like I said, does not determine the limit by its appearance alone. So when you get 0/0, it may not necessarily be the answer to the limit. So sometimes you may have to go ahead and do some things. For example, if the function is x squared minus 1, you know that the numerator here is difference of 2 squares. But if you do direct substitution, if you put 1 here, 1 squared will give you 1, 1 minus 1 will give you 0. If you also place 1 here, 1 minus 1 will give you 0. So it gives you an answer of 0/0. And this does not necessarily mean that the answer is supposed to be like this. So using factorization method, you realize that the numerator will have factors of difference of 2 squared, x plus 1 and x minus 1. And it will cancel one of the denominators. That will leave the function to be equal to x plus 1. Now, when you substitute x equal to 1, now your limit is now 2. So the point here is that sometimes indeterminate form does not determine the limit by its appearance alone. Okay, so just giving you this may not necessarily be the limit. Okay. So here, these are the 7. Okay, there are 7 forms of indeterminate form. So kindly take note of them. The 0/0 is a popular one. Infinity over affinity is also very popular. I'm not too sure whether we've seen this type we have the product and the difference forms. Product means that 0 is multiplying infinity, and then infinity is subtracting from infinity. This is also another form of indeterminate form. Then the exponential form is 0 raised to the power 0, 1 raised to the power infinity, and infinity raised to the power 0. So what we are saying is that these 7 methods, the 7 forms, 1, 2, 3, 4, 5, 6, and 7. If you solve a problem and it gives you that, then you must do further simplification. That's the point we are making. Okay, so identify this, and then you go on and do simplify with the techniques we are going to learn this morning. So why is 0 over 0 indeterminate? So they gave examples. So for example, if you have x over x and you substitute 0, we are assuming that even though the result would have given you 0 over 0, actually the function should be approaching 1 when you solve it. So we are telling you why we have to use indeterminate form analysis to look at problems like this: x over x, x squared over x, and then x over x squared. Some of the answers will give you unbounded solutions. So all initial display of 0 over 0 by their limits behavior differs. So sometimes when you get 0 over 0, the behavior of the function may not necessarily be the same. So 0 over 0 is not an answer. It is a signal for further analysis. Okay, so we have laid the foundation for why this topic indeterminate form, we must spend time to analyze it. Don't be quick to jump to the conclusion that the answer is correct. Okay, so let's take the first technique. I think there are 3 or 4 techniques. The factorization one, this is the one which is very familiar to us, very easy to identify. So the numerator is difference of 2 squares. So that will give you x minus 1, x minus 3, x plus 3. So if you substitute into that, then the x minus 3 will cancel the x minus 3 in the denominator. So the numerator alone will be left with x plus 3. And then if you substitute x equal to 3, 3 plus 3 will give you 6. So this is for factorization technique that I'm sure we are familiar with. Then the same factorization technique, the function is the numerator of the function. You must be careful. This is to the power 3. So you must also realize that you can factorize this. And the x cubed minus this, we call this the difference of cubes. We have difference of squares. A difference of cubes, it gives you, one of them will be a linear function. The other one is going to be a quadratic function. So the numerator x cubed minus 8 will give you x minus 2, x squared plus 2x plus 4. So if you substitute the numerator with these factors, then you see that one of the factors will cancel the denominator, and then you'll be left with the numerator as x squared, 2x plus 4. Then substitute the limits, and that will give you 12. So we've seen factorization with difference of squares. We've seen factorization in difference of cubes, okay? And then there is also a second type of technique that we call rationalization. Now, rationalization, I hope you haven't forgotten complex numbers. We learned that method in complex numbers. When you are given a problem and the numerator seems to have square root signs in there, then the method to do this is to rationalize. This morning, I went through the slide and I felt we need to do this together so that if you have forgotten, you can remember. So rationalizing means that you multiply the numerator and denominator by the conjugate. Remember that the original question is minus here. So the conjugate will be plus. So I have placed the plus 1 by each side. So I multiply the numerator and the denominator by this. And if you remember what do you call it? The method of multiplying the conjugate, the numerator is going to be the first term squared minus actually the second term squared. Okay, so minus 1 raised to the power 2. Okay. Now, then as for the denominator, it will remain the same way as it is. There's nothing you can do about it. The denominator remains the same way as it is. Now, if you solve the numerator, then you realize that the square root sign will go away. Then we're left with 1 plus x, because this is supposed to be this times this. So you will have 1 plus x or minus 1. So, and then the denominator will remain the same. Now, if you simplify this again, you know that the numerator will give you x over what we have right now. Okay. Now, if you now substitute x, and then the numerator, the numerator of the x will cancel the denominator of the x. So you'll be left with 1 divided by the term in the square root sign, this term. Okay, so now if you substitute x is equal to 0, then the numerator will be 1 and the denominator will be 1 plus 0. Okay, we are doing it together. So we are getting square root of, remember there's a square root sign. Square root of, if I place 0 here, it will be square root of 1. And square root of 1 is 1. So you end up getting 1 plus 1. So finally, this answer will give you 1 over 2. Please, is there any question with respect to this? I'm hoping that you remember the use of conjugates. So multiplying the numerator and the denominator, we end up getting rid of the square root in the numerator. And then it ceases to be a square root anymore. Then you can now simplify by canceling the numerator x over the denominator x. And whatever is left, whatever function is left, you can now substitute the value of x, the limit. Then that gives you this. So the technique of rationalization comes into play when the function happens to have either things in the square and the square root sign. Then the best method is to rationalize. Okay, so we've seen factorization, we've seen rationalization. Now, then the third one is to use what we call the standard trig limit. So you may be given a question and there will be trig functions in there. So when you are given that, how do you approach it? Again, this one too, I think we should try and do it ourselves. So they are telling us that there are some standards of trigs. Sin x over x, when you use the limit equals to 0, it will give you 1. These are standards. If you get a constant multiplying tan x over x, okay, if the argument of the trig function is the same, the value of the argument is the same as the divisor, then always you get 1. So you see that the argument of sine is x, the divisor is x, then the function is 1. If the values are the same, so if it's not x and it is 10x and the denominator is 10x, it will still be the same 1. So for tan, again, you have a constant multiplying tan x all over x will give you 1. And then for cos, if you have 1 minus cos x over x squared, these are standards, the limit will give you a half. So angles must be in radians to do this. Then we are given a question. This is actually a question. It says that find the limit as x approaches 0, sin 5x over x. Make sure that the answer is giving you 5. That is the question. So how do we go about this? So like the theorem said, if the numerator function, sign of that function is equal to the denominator function, then the answer will be equal to what we have here. So how do we approach this? Now here, I've given you the approach. So number one, this is the question. If we want to use the standards of trig, which we have seen before, we already know that sin x over x is 1. We know that. So now let's rewrite this question so that the numerator angle will be equal to the denominator function. We want it to look like this. Okay, So this is how we are going to go through it. Okay, so now we are, I think, 11. That's good. I can see Philip now and Joe, Raphael. Okay, so I hope you haven't missed much. We are revising certain methods of indeterminate form. So let's take the equation here. How can I write sine 5x over x to look like sine 5x over 5x? How can I do that? Very simple. Just, so it means that this is a question. I want 5x here. We want to have 5x here. And I also want to have 5x here. The only way I can have 5 in the denominator is to multiply the numerator by 5. I hope you agree. Because if I multiply the denominator by 5, this 5 will cancel this 5, and it goes back to the question itself. Okay? It goes back to the question. So the trick is that when you are given the function and the numerator of the sine function, the argument, the angle of the sine function is not equal to the denominator, then you must introduce a constant that can multiply the denominator so that it can look exactly like that of the argument of the trig function. Now, when we do that, then you know that this 5 is a constant. 5 doesn't depend on x. So 5 can go out there and multiply the function. Now, the function will be like exactly what we want, 5x over 5x. Okay? So now that the angle of sine is the same as the divisor, then I know that this simply is going to be equal to 5 times 1. I hope you know that this, I don't need this one here anymore when I do this. Okay, so then it means that already I know that sine x over x is equal to 1. So sine 5x over 5x will also give me 1. So the answer will be 5. This is a 5 for the factored value, all times 1, according to the standard of sine. So the answer to this trig function should be 1. Okay, so the problem or the question is that if the problem is given to you and you are not sure of what to do, first of all, check the standard for that function. So I'm saying that if, for example, this is, let's say, 10x, okay, then we will go out of the route and know that I must be able to rewrite this so that the numerator angle will be equal to the denominator angle in denominator function. So I'm sure when you follow this, you will know that this simply will be equal to 10. The answer will be equal to 10 times 1. Okay, Philip, you have your hand up. What's your question, please?
Good morning, sir.
Good morning. Welcome.
I'm fine, sir. Sir, I heard that you said we should by the end of the solution we should get 5, but now we get 1.
Oh, sorry. Why did I write 1? Sorry about that. It should be 5, not 1. Obviously, 5 times 1 will give you 5, not 1. Okay. So that should be our way of approaching questions like this. So anytime you see a trig function, just remember the standards. Please, these are the standards. Sin x over x is 1. A tan x over x is 1. 1 minus cos x over x squared is 1 over 2. I just hope questions that you will come across are familiar standards that you are aware of, then you know what to do. Okay, so we've seen factorization, we've seen rationalization, we've seen use of standard trig function. Okay, now we want to interrogate the other forms of indeterminate. So we've seen some types. So first of all, we've seen 0 over 0. So let's say infinity over infinity. Now, so when you have x approaching infinity in a rational function, that is a numerator and a denominator, compare the dominant powers or divide by the highest relevant power. So for example, this one, you see that the dominant power here is x squared, and that of the numerator is also x squared. So obviously, if you if we look at the rules, the answer will be the coefficient of since the powers are the same, the answer will be equal to the coefficient of x squared, so 3 over 5. So this is an example. Because if you try direct substitution, you end up getting infinity over infinity, which is what we are calling indeterminate form. So then we use the techniques of the powers of the polynomial in the numerator and the denominator. So now these are the analysis. If the degree of the numerator, 1, is less than the degree of the denominator, 2, then we say that the limit is 0. This one is actually one of the things we have in rational functions. We are given a rational function, the numerator is less than that of the denominator, then we know that the limit will always be equal to 0. Now, but if the degrees are equal, this is what we just saw a few minutes ago. If the degrees are equal, like we're saying here, then it becomes the ratio of the leading coefficients. That's why the previous one we got 3 over 5, because the leading coefficient of x squared is 3 here, that of x squared here is 5 there. Now, then the third one, if the degree of the numerator now is greater, so we have less than, equal to, and then greater than, then you must usually have an unbounded function, and therefore you must inspect the sign and the behavior. So, for example, we have x in the numerator, and you have x squared in the denominator. Now, if you try to substitute the limit of infinity, you still end up infinity over infinity. But they're telling us that we must check for boundedness. So end up getting 0. We'll see an example to explain this further. Okay, so we are looking at the other type. So we've seen infinity times infinity. Now let's see an example of infinity multiplying 0. Now, if you get a product approaching 0 multiplying infinity, it's also on an indeterminate format. The first thing you need to do is rewrite it as a quotient. So maybe something you were given, this is, for example, x natural log of x, okay? X natural log of x. So for us to be able to solve this, because if I put infinity here, I'll get, sorry, is it infinity? If I put 0 here, I'll end up get 0, 0 multiply infinity. So we must look at what happens as x approaches 0 from the positive end. So this thing can be written as, okay, this one can be written as natural log of x over 1 over x. I hope you can see that 1 over x will go back to look like this, because the x will come back and multiply this. That is a method. It says when we do that, we have to look at the technique. It says when we happen to have this approaching this, then rewrite it as a quotient. So rewrite it as a fraction. So we have a product of a function. I've written it as a fraction of a function. This produces a quotient form suitable for further analysis. So here, maybe then we may have to take the differential functions or something to do this. So that is for problems that looks like this. Can the function be rewritten so that it looks like a fraction? Then do that. Then when we have infinity multiply infinity, you must first of all transform before evaluating, because if you evaluate directly, you will not get the correct answer. So the methods involved in this are combined fractions, rationals, radicals, or factor dominant terms. So answers that gives you this, there may be some fractions must be combined, or you must rationalize, or you must factor. The difference of two unbounded quantities may have finite limit. This value is unbounded. Infinity is unbounded. It means you are getting a value that is not ending. So when you get these types of answers, you must take these steps to be able to evaluate them. Okay, so there is one question here, and I want to see how to go about this. So if you substitute, like we are saying, if you substitute infinity into this, we'll get infinity minus infinity. Okay, and so the best way, like you are saying, is to use the method of conjugate. Conjugate is rationalizing. Now, if I multiply this function by its conjugate, then you see that the conjugate will be plus. That is why, and the numerator here, I'm sure this sender should be over x. Multiply the numerator and denominator by 8. So I multiply the numerator x squared plus x into bracket minus x times this same thing, x squared plus x, this time plus x. When you do that, the numerator will reduce to this, okay? And you end up getting x squared plus x over this. Now, if I divide by x, I'm going to get 1 over this whole thing. Then now I can substitute infinity into the function. 1 over infinity, I hope you know that 1 over infinity will give you, what's the value of 1 over infinity? That will give you, I think, 0. So 1 plus 1 in the denominator will give you 2. And the numerator will give you 1. Okay, so we are approaching the questions or each of the questions you get, you must check what format of indeterminate you get to identify the correct method to use. Now, the last part of the 7 methods are the exponential ones. What if you get 0 raised to the power 0, 1 raised to the power infinity, and 0 raised to the power infinity? Now, an example is this. If you are given a function y and it's equal to f of x raised to the power g of x, that means a function raised to the power of a function, then the method is to take log on both sides. So remember this technique. You take log on both sides. So log of y becomes, we are using natural log of y. And then if you take natural log of f of x, we get the power coming to multiply g of x times natural log of f of x. When you evaluate, you realize that the transform function will be y is equal to, and it's the constant e raised to the power, the limit of the value. These are all type of techniques for these type of questions. There's an example here. I didn't expand the example, but you can take a comment. Now, this was the limit function. So according to the standard, we let y be equal to that equation. Now, if I take natural log of y, I'll get natural log of y here. And if I take natural log of this, I'm going to get lane 1 plus x all over x. Remember, this 1 over x will come to multiply. That is why it comes in the denominator. Now, at this point, if you substitute x equal to 0, you will still end up getting something you don't want. So we will differentiate. That's why I've written here. The method to approach is differentiate the numerator with respect to x, differentiate the denominator with respect to x. When you do that, you end up getting this solution. If you've forgotten how to do this, I will try and send you the steps to this. I felt the material was becoming large, so I jumped some steps. So the answer should give you E. So now we are virtually summarizing and therefore comparing indeterminate format to undefined format. So 0 over 0 and infinity over infinity are indefinite. But when you have a non-zero numerator, for example, I get 4 over 0, then that is called undefined. It's not one of the 7 standard indeterminate form. So this one, when you get things like this, you must study the behavior of the function from one side or the other side. So that's one. Another example is when I evaluate and I get infinity plus infinity. So generally, this is also not indeterminate when the signs are compatible. So always distinguish between the symbolic form from the actual existence of limits. So this is a summary of the indeterminate types, and then answers you can get that look like indeterminate, but they are not. We call them undefined. So the strategy for this indeterminate are these 8 points. First of all, when you are given the problem, try direct substitution. Then secondly, identify the results you get. So the results you get, are they in the format of the 7 I have mentioned? If they are, for 0 over 0, you factorize or you rationalize, simplify, or use standard limits. For infinity over infinity, compare dominant terms. For 0 times infinity, rewrite as a quotient. And for infinity minus infinity, combine or rationalize. So exponential form use log, and then you can check for one side domain for functions. So this is a summary of all that I have talked about in the past 30 minutes for each of the indeterminate format you get. Okay, so what is the engineer application? Like I said, the last session 3 is about engineering of all these topics. So we say that indeterminate limits arises for instantaneous velocity or strain and heat transfer gradients. So any gadgets that may use any of these properties, then we can see that we may end up getting results that looks like indeterminate. They also occur in asymptotic systems, and they respond to high frequency approximations. Okay. And then dominant term analysis helps to simplify large-scale engineering models. So limits also support error analysis and numerical approximations. Okay, so these are the areas in which this particular analysis of in mathematics called indeterminate can help us solve problems in engineering. All you need to do is to identify whether the engineering problem conforms to some of these standards. Now we end with some solved problems. I won't have the time to do them manually because we've seen quite a lot of them before. So the first one, you use factorization. I hope you can see it. The second one, you use rationalization. The third one, this is cubic function. So you try and see whether you can factorize. Sorry, the third one, I think you must look at the dominant powers of the polynomial. So x cubed. So you get 7/2. The fourth one, remember, you might get standard for sign. So if you can rewrite the denominator as 3x, then you can end up getting the limits. And then the last one too is example to the number 2, where you are looking at possibly rationalizing to solve your problem. There are 2 questions here. Here, this one is saying identify the form and choose the best fit method. So when you look at it, you tell which method will help you to solve the limit equations that you have. Okay, so that's the first one. I told you that there are actually 4 topics I'm doing this morning. So kindly take note of it and see whether you can use the analysis that I've given to solve this. I have solutions to all this. I have them. So if you try them and you need them, I can send them to you to compare your answers. And so these are the summary of indeterminate. Let's come to L'Hopital. This one too, we saw it last semester. This one will be shorter than indeterminate because we've seen it before. What are we looking for? Now, L'Hopital rule, first of all, we want to look at the rule and then look at how it affects limits. Then we distinguish again between these 2 types of limits and also what rule to use. And L'Hopital rule, one thing you can do is that you can apply the rule repeatedly. If it's differentiation, you can differentiate first time, second time, sometimes even the third time to see whether your answers are justified. And then if you have questions that gives you limits as 0 times infinity and infinity minus infinity, then like we did for indeterminate, we may use exponential form to solve our problem. And some of these things we have engineer application. So these are the we are reviewing what we saw in indeterminate. So we are saying that number 1, 2 quotient forms central to L'Hopital's are this 0/0 and then the infinity/infinity. So first of all, try direct alone. If it doesn't work, then we may use algebraic simplification, which may work faster for us. Now, this is the L'Hopital rule. If a function is dividing another function, and the function is giving you the 2 forms of the quotient indeterminate, that is 0/0 or infinity/infinity, then the rule says that differentiate the numerator and then differentiate the denominator and see whether when you substitute the limit, it gives you a bound as a value like L. And if this bound is finite or infinite, then you must undergo conditions. What are the conditions you undergo? You will substitute that same limit into the original equation to see whether it gives you that same boundedness. So that is the technique of L'Hopital. Differentiate the numerator and denominator and check the answer you get. Basically, that is that. So the expression must be a quotient. So we apply L'Hopital rule for only fractions. And then direct substitution must give you this first before you go on and use L'Hopital. Numerator and denominator must be differentiable on the appropriate interval. And then the denominator must not disappear. They must not vanish. If the denominator vanishes, then the L'Hopital rule is not helping us. And then the derivative ratio limit must exist. So the L, when you find the differentials, and then you get the ratio, that value must exist. If it doesn't exist, then we are having an unfortunate behavior of the limits. We may have to use another technique. So that's an example of 0/0 indeterminate. So sin x over x. If you do direct substitution, sin x will give you 0, and then you get 0/0. Immediately, we must apply L'Hopital rule here. So we differentiate the numerator. Sin will give you cos, and differentiate x, it gives us 1. Now, when we substitute x equal to 0, we end up getting cos 0 is equal to 1. So this is one example of 0/0. Then the second one, this time we are having a difference of 2 squares. Again, if you substitute directly, it will give us exactly this. Now, in indeterminate, we could factorize, what do we call it, using difference of 2 squares to solve this. But here we are using L'Hopital. So L'Hopital says that let's differentiate. If you differentiate the numerator, we get 2x. You differentiate the denominator, you get 1. Now substitute 2 into it, and you get the same answer. So note, factorizing also gives you the answer efficiently. This is also another type, example, exponential type. Again, if you substitute directly, you get 0/0. So differentiate the numerator. If you differentiate the numerator, you still get ex. Differentiate the denominator, you get 1. Then substitute the limit 0. E raised to the power 0 will give you 1/1, and the answer is 1. Okay, so L'Hopital, for that, I think is quite direct. You must always be able to check the original substitution of the limit. If it doesn't work, then differentiate the numerator and denominator, and then you get your answers. Okay. This is an example of infinity over infinity. Again, if you do this, you end up getting infinity over infinity. But if we differentiate the first time, 3x squared will give us 6x. And then 2x squared will give you 4x. Again, if you substitute infinity into this, we still will get infinity over infinity. So L'Hopital says that differentiate again. And if I differentiate again, you see that I'll get 6/4, and which gives me 3/2. It is equal to using the indeterminate method where we said if the powers of x are the same for the numerator and denominator, then you use the coefficient. You see that we are getting the same answer. Okay, so all these techniques, they must actually help each other to solve a problem when you are given it. Now, so repeated applications, example, this one will give you a repeated application, 1 minus cos x. If I differentiate this, first differential will give me sin x. Negative cos x, if you differentiate, it gives you sin x. And you differentiate x squared, it will give you 2x. Again, when you substitute the value of x equal to 0, you get, again, another 0/0. So differentiate sin x again. That will give you cos x over 2. So first differential give us still indeterminate. Second differential give us answer. So we are saying repeated application of L'Hopital rule sometimes helps to solve the problem. So when not to use L'Hopital rule, do not apply rule directly to questions like 0 times infinity, infinity minus infinity, 0 raised to the power 0, 1 raised to the power infinity, and infinity raised to the power 0. Please don't do that. First of all, transform them into the suitable quotient or logarithm format. Then the L'Hopital rule can apply. So Remember, we saw this example in the indeterminate. X ln x can be written as ln x over 1 over x. Direct substitution will now give you infinity over this. So we differentiate ln x, it gives us 1 over x. You differentiate 1 over x, it gives us negative 1 over x squared. Again, this time, when you cancel, you end up getting minus x. So when you put x equal to 0, x approaching 0 from positive side, you end up getting the answer to be equal to 0. Okay, so transform them when they are in the format like we have said here, these formats. You must transform the question before you apply L'Hopital. Okay, so this is also another one. So for this one, we found the LCM, and then we solve, and then we ended up getting the numerator to be equal to this, the numerator to be equal to that. Before, we ended up getting this. With this one, if you substitute infinity over infinity, so you must differentiate. The numerator becomes 1, the denominator becomes 1. Okay, so all these are explaining the various methods. Then we have the exponential form too. This one, we saw it in the indeterminate form. So I think we can go on. There's an example here. So you take y, you let y be equal to the function, take natural log of the function, and then you differentiate. Okay, this is an example too here. This one gives us e raised to the power y is to the power 0 when we differentiated the function. So L'Hopital rule can apply to one-sided functions like x approaching infinity, positive infinity, or negative infinity. So always check the original form, and then logarithm and radicals may impose one-sided restrictions. Okay. So these are the common errors that students sometimes face. Instead of applying L'Hopital rule, they will do direct substitution. So first of all, differentiate the entire quotient using the quotient rule, and or differentiating numerator and denominator separately. Forgetting to recheck the form after one application, and then ignoring the domain restrictions. Use a rule when you have simpler algebra. It is more efficient. Okay, so that is for L'Hopital rule. And basically, these are the procedure. You substitute, you verify, you differentiate, you reevaluate, you repeat differentiation, and then you check for other forms of indeterminate form. Now, what is the application for L'Hopital rule? Again, it supports asymptotic analysis in engineering, how transfer functions behave, growth decay ratios, signal responses limits, rate of comparisons, and approximation error analysis. Okay, so these are some applications which we can apply this rule in. I think I'm left with 2 more to go. So please, again, there are exercises here, and I have solutions to all these as well. Some MCQs, and this is a summary. Now, there are 2 more I need to show you, Rolle's theorem and MVT. Rolle's theorem, this is also very, very simple. It's not that difficult. Let's look at the rule. This and the next theorem are very similar. This one solves problems using what we call specific value. And then the last one, MVT, mean value theorem, will look at a range. So let's go through it. What are we supposed to know in Rolle's theorem? What does the theorem say? How does it explain geometric meaning? Okay. And then we have to verify continuity and differentiability, and then find what we call the differential at a particular point. Determine whether this theorem does apply. So you see at the bottom you have written, Rolle's theorem connects to mean value theorem and engineering interpretation. They actually linked together, but I have separated them. So when we'll go through the 2, you can see their differences. So what does Rolle's theorem do? It's actually one of the foundational results in differential calculus. All these things you are learning is because of differentiation. That's why this course is called calculus. So much of differentiation and integration. Now, it guarantees at least that there is one stationary point between some endpoints. And it's also a special case for mean value theorem. So this is a historical background. So now that is the method, that is the technique, or that is a theorem. It says that if you are given a function, check whether the function is continuous. What does it mean? You must substitute the values into the equation, see whether they exist, something like that. So check whether the function is continuous within the interval that is given. Then number two, differentiate the function and see within the same interval. And check whether the interval f of a and f of b, the answers are the same. Function of a is equal to function of b. And then the last thing is to show that the point C exists. There's a third point that will exist within the interval that is given in question. Okay? Please, the step seems to be a lot, but when you see a question, you appreciate that, oh, this thing is not as difficult as it is. So let's take, first of all, let's look at this interpretation, and we take an example. If you are given a smooth curve, if a smooth curve begins and ends at the same interval, in the same vertical height, then somewhere between the endpoints, it may have a horizontal tangent. Okay, so look, for example, if I draw a parabolic function, then you know that parabolic, there's the minimum turning point. The curve is going to end either in the upper region of the y-axis. So they are telling us that between the endpoint, there must be a middle point where you can find a horizontal tangent. So pictorially or geometrically, that is the interpretation of Rolle's theorem. So the Rolle's theorem guarantees existence, that there is a value between the interval. And it does not necessarily identify a unique point, but it just tells you there must be a point. Okay, and then it also tells us that for you to use Rolle's theorem, the interval must be continuous. If there is a break, or there are jumps, or there are holes, it will destroy the whole geometric conclusion we are drawing. So please, we don't use this for functions that are not continuous. We only use it for equations that are continuous. And then there is an interval that supports the hypothesis. Differentiability rules must happen. And then you must check for vertical tangents, as well as the point in which that tangents occur. The condition is that the endpoint f of a must be equal to f of b. And that is the secant. I hope you know secant, the slope between the endpoints. And Rolle's theorem guarantees an interior tangent. There are too many literature here. Let's take a question and then we will understand all this. So check for continuity, check differentiability, check for verify the endpoints, differentiate the function, substitute the point at the differential, and make sure it is within the interval. Okay, so please, if you want to solve Rolle's theorem, these 5 steps you must do. So let's take an example. Verify Rolle's theorem for x squared 4x plus 3 quadratic equation. And then these are the interval. First of all, how do we verify that this is continuous? Obviously, this is a quadratic equation. And polynomials we know are continuous. They don't break anywhere. So that is our verification. Polynomials are continuous and they are differentiable. So we have verified step 1. Remember, step 1 is check continuity. So polynomials are continuous. And then check differentiability. Polynomials are differentiable. So we done step 1, step 2 by identifying the type of function. Now step 3, let's substitute the limit, the interval, into the function. If I put 1 here, 1 squared is 1. Minus 4 times 1 will give you minus 3. Minus 3 plus 3 will give you 0. So f of 1 will give you 0. Now, when you substitute 3 into the equation, 3 squared is 9. And then 4 times 3 is 12. 9 minus 12 plus 3 will also give you 0. So we have identified that f of 1 is equal to f of 3. That is step 3. Now, step 4 is differentiate this function. If you differentiate x squared, you get 2x. Then differentiate minus 4x, you get minus 4. Then remember, they said then you equate f of f and the differential of x into 0. So if I equate 2x minus 4 to 0, I'm going to get x is equal to 2. Oh, sorry, C is equal to 2. That means I am actually evaluating the value of f of x at 0. Now we can conclude that this value 2 is in the interval 1, 3. This is all Euler's theorem is saying. Okay, so all this big English we have read, all that is saying that when you are given the equation, check that the function is continuous, check that it's differentiable, evaluate the interval on the function, and then when you differentiate, the answer you get, see whether it's in the interval. Basically, that is Euler's theorem. Okay, another example. This time, my values are -2 and 2. So again, difference of 2 squares, we know it's a polynomial, so it's continuous. If you substitute -2 and 2, the answer will be 0. So that is step 3. Differential of 2x squared will give you 2x. Okay? If I equate 2x to 0, I will end up getting c is equal to 0. And you know that the value 0 is in the interval -2 and 2. Okay? I hope these things are straightforward. I know if you have a question, you raise your hand, but let me know if something is not clear. I'll go over it. But I think these theorems and these techniques are quite self-explanatory if you understand what the theorem is saying. The third example, this is a trig equation, a trig function. So remember, what is a sine function? You know, sine function is a sinusoidal. Okay, it's going up and it's coming down, it's going up and coming down within 0 and pi. So what do we do? Because it is a sine function, we know it's continuous. And then we know we can differentiate sine. Now let's evaluate sine 0. Sine 0 will give you 0. What is sine pi? Sine pi will also give you 0. It means that the intervals gives you the same answer. Now let's differentiate sine. Sine will give you cos. If we equate cos x to 0, we end up getting x to be equal to cos inverse of 0. That means that we are finding c. And cos inverse of 0 will give you pi on 2. And pi on 2 will lie in between 0 and pi. Okay, so Euler's theorem, it works. It works. Okay, and we haven't done mean value theorem, but now they are comparing it to mean value theorem. Maybe you may not understand this particular slide till I do mean value theorem, but they are telling you that Euler's theorem is actually very similar to mean value theorem. That the endpoint may differ, equals the average of the slope. Let's not worry too much about this. I'm going to do that as the last thing for today. So basically, these are some examples of questions. So you will first of all check the equation. This quadratic is continuous. Check whether it's differentiable and make sure that when you differentiate this and equate to 0, the answer will be in between 2 and 3. Do the same thing for cos x and do the same thing for x cubed minus this. Okay, so these are very good examples to practice to make sure you follow through with this and some more trial questions. So that's the summary, and it tells us exactly what I have explained. Now the last one, mean value theorem, this one. So what is the difference between this mean value theorem? First of all, verify again the continuity and differentiability, and then find the point C as well, point or points. Sometimes you get more than one point. Explain the geometric and distinguish between this. Okay, so similar to that of the Euler's theorem. So for Euler's theorem, this is what we did. We were given an interval. We evaluated the function at the interval and show that the point exists. And we are saying that mean value theorem actually will generalize the Euler's theorem for us. That is what mean value theorem would do. So this is a rule. Please see, look at the difference. The other one, you will first of all find out whether the interval is continuous, and then you differentiate and then show that there's a point in the interval. That's Euler's theorem. But for mean value theorem, you go further and then you find the slope. What's the slope? I hope you know slope is dy dx, and the y differences over the x differences. So here, the interval they've given us. Now, we must show that the differential at C should be within substituting B into the function of B, and then substituting A into the function of A, all divided by the value of the interval. If you're able to show that this exists, then we are saying that mean value theorem has been proven. So this is saying that the rate of change equals to average rate of change at the interior point. So that is a difference, the only difference that you have between Rolle's theorem and mean value theorem. Then they are explaining further here. So how do we go about it? Confirm that the function is continuous. 2, confirm that it's differentiable. 3, compute the average. So mean value theorem, you must compute the slope or the average and show that the slope is equal to the differential at that point. So let's try some examples. Let's see this example. Okay, so my original equation is f of x equal to x squared. Okay, now this is quadratic, so we know that it is continuous. Number 2, it's also differentiable. Now, let's find the slope. Remember, slope is saying that you substitute the values of the limits into the equation. So what is f of 1? F of 3. If I place 3 into this equation, I didn't do it here. I hope you can see. What is f of 3? 3 here will be 3 squared. That gives me 9. If I substitute 1 squared, that will give you 1. So 9 minus 1 is going to give me 8. All divided by b minus a. b minus a is 3 minus 1. And 3 minus 1 is 2. So 8 over 2 is going to give me 4. So we have evaluated the function, the slope. Now let's differentiate this equation. If we differentiate x squared, we get 2x. Now, it means that we are saying that this is our point C, 2C. So this 2C must be in the slope. So if I equate 2C to be equal to 4, I will end up getting C is equal to 2. And this value 2 will be in the interval 1 and 3. Okay, so it's similar to Rolle's theorem, but here we have to find the slope and equate the slope to the differential and show that the answer we get will be in the interval given. Okay, so that is an example of a mean value theorem. There's another example here. Again, for the slope for this, what is 2 raised to the power 3? 2 raised to the power 3 will give me 8. That's for this one. And then when I substitute minus 1 raised to the power 3, I'm going to get negative 1. So 8 minus 1 is going to give me 9. Then all divided by 2 minus 1, that gives you 3. 9 divided by 3 will give me 3. So that's the slope, average slope. Then we differentiate x cubed. That gives us 3x squared. We equate that. We substitute x equal to c. We get 3c squared is equal to 3. That gives us that c squared is equal to plus or minus 1. Because c squared will be equal to 1. 5 squared will give you plus or minus 1. And you know that only the value 1 can be in the interval minus 1 and 2. So it means that negative 1 will be excluded in the endpoint. Okay, so there's a third example, this time a trig function. So we substitute 0 into sine x. Sine 0 will give you 1. Then sine pi on 2 will give you 0. So 1 minus 0 over pi on 2, that gives you 2 over pi. Then when we differentiate sine x, we get cos x. And if we make c the subject, cos c is equal to 2 over pi, so it will be equal to cos inverse of that. And the answer will lie in between 0 and 2 pi. So all the 3 examples, you find the interval, find the slope, differentiate and equate the function, the differential to the interval, and show that the interval exists. Okay, so in summary, Rolle's endpoint values are equal. So the average slope will always be equal to this. And then you are able to evaluate that value, C. A mean value theorem, endpoint values may differ. So f differential is equals to the secant, or the line of the slope. Therefore, Euler's theorem is a special case of a mean value theorem, like we said in the previous slide. Okay. Then there are some things you need to take care of. Sometimes you may get error approximation. When you differentiate the function and it's less than the mean value theorem on the interval, and then also when you find the slope and also less than the mean value theorem times b minus a, these are some errors and approximation that you can use. This inequality is useful for sensitivity and error propagation in engineering estimates. Okay, so this is some application to the MVT. Okay. Then they give a worked example of this. I won't go too much into this. If you want the details of this, it's also in the solution I have. So again, how do we go about mean value theorem? Identify the interval, check for continuity and differentiability, calculate the slope, differentiate the function, equate f, the slope, equate the differential of the point to the slope, and then solve for that point and make sure it's in the interval. Okay, and then you have these exercises that you can try your hands on. Okay, so in the summary, that is what I have for you. A lot. I'm sorry, the slide is a lot. If I continue to add one, I'm sure the slide will go beyond 100. But I wanted all to be in one document so that when we take unit 3 or unit 4, I'll do the same with unit 4 and 5. As for unit 6, it's just mainly a lot of applications. So hopefully by next week, I should be done, or hopefully by first week, I should be done with all this, so that you will have time to be able to practice with the quizzes and prepare for your exam somewhere in September, I'm sure, somewhere there. Okay, any questions from today? I don't think today I've done something that is that difficult, but I don't know. Any questions? Hello, are you guys there?
Yes, sir, we are here.
So we are
Okay.
here.
Okay. So, like I said, the more we solve questions, the better it becomes. So, on the elements, like I did for the others, I've also created some worksheets that can help you to be familiar with it. Some of the worksheets, the solutions are there. So let me show you almost all of them, and then so let's start from mean value theorem. Okay, so the indeterminate form. So this is a worksheet evaluating using the factorizing method. So example, evaluate this limit. Remember this, you can use difference of two squares. Please, for this one, I think there are 16 questions. 16. Oh, more than 16. I think 20 questions. But all of them have been solved. All of them have been solved. So this is to help you to be able to, first of all, make sure that you understand the terminologies, understand the technique for indeterminate form, and then how it is used. So each one has been solved, and they've given you detailed solution. It's not like my third worksheet. For that, they give you the answers, but this one, it has the detailed solution. So what do you do? First, attempt to evaluate the thing directly, like I said. And then when you identify the indeterminate form, then we know what to do. Whether we need to use difference of two squares, we do that. Okay, so this is quite detailed. All the 20 questions have been solved, and it's in the worksheet. Now, the second one, okay, the first one, tells you the various techniques we saw, and when do we use direct indeterminate, and when do we use L'Hopital rule. Okay, so for this one, the solutions are not there, but if you want them, I can generate them for you. So you have problems like this. We've seen examples like this today. So this is taking this will take care of the L'Hopital rule. And then the last one, I think, is the mean value theorem. And for that, you have the solutions at the bottom. So please look at the graphs have been given, and it's been plotted to know that, number one, the functions are continuous and they are differentiable. Okay, they are continuous and they are differentiable. So this is a quadratic equation, and it tells you that this is also a cubic function. And so what do? You first of all will evaluate and find the slope. And when you're done with the slope, then you will now differentiate and see whether the answers you get can be within the interval that have been given. So question 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And for each problem, determine if the mean value can be applied. If it can, then find values of C that satisfy the theorem. If not, explain why not. Okay. So these are the questions, and like I said, the answers have been provided.
Yeah.
So for these ones, we don't have we don't have the detailed solutions, but at least if you're able to solve them, you can compare your solutions to what they have to be able to know whether you're on the right path or not. Okay, so that is the slide, and then the materials on Unit 3. And like I said, all of them are on the LMS. And then when you come to the quizzes, you see that you have 15 questions on all the things that we've done. So kindly take advantage of the materials. I hope by next week, the other 2 quizzes should be there as well. I want to make sure you have enough time to be able to revise for your exams. And then hopefully your midterm. I'm creating them, but getting document type is not that easy. So you realize I have created that of Unit 4 and Unit 5 and Unit 6. Unit 6 is vector analysis. We did vectors last semester, so I hope that one will go quite well. So it's rather Unit 5 and Unit 4. We'll review some integrations that we did last semester, and then this will take us to what we call applications to integration, but higher order differentiation. We need to know a few of them, what we call partial differentials, higher order differentials, and all that. Then at the bottom, at the end, you will have your midterm. So I'm saying that the mid-semester questions will come from all these question banks which I have created. The question banks are being created gradually. You can see that it takes time to do them. So when I'm able to create the questions, see right now, maximum you have 120 questions. Parametric, you have 120 questions. And what I did on indeterminate, you have 343 questions. So when I'm done with all the topics, then we pick, let's say 555 from each, or 10, 10, 10 from each. And that becomes your mid-semester exams. Okay, so that is what I have for you today. Sorry about the detail. I don't like long PowerPoint, but I don't want to have separate PowerPoints for these topics. You can separate them if you want to. I want the materials to be under units so that if you convert it into even Word documents, you can have a whole lecture materials on them at a go. Okay, so if there are no questions or comments, then I'll leave you guys to prepare for your next class. I think I have spoken a lot, and there's a lot in here which you need to have time to prepare for. By the way, how many midterms have you written? Have you written any at all?
Sir, in the other courses,
Yes.
no, we haven't written it.
Okay, okay. So I'll just measure myself with my colleagues whether I'm the only one behind, but I think we are all within the same. This I saw your calendar, so I think we have, is it 2 or 3 more sessions, and we have our last face-to-face class. So I hope within the 2 or 3 we can be able to finish the main topics. And when we meet physically, we'll just use it to solve as many questions for your exams. So thanks for coming.
And uh, and next week I think it will be self study.
Yes, I saw it. I saw it as well. So whatever it is, I'm sure the if I'm able to get your quizzes, talking about the 15-minute quizzes within the on the LMS, then you can use that to at least go through the materials. Yes. So we don't
Yes.
lose completely on the week. Okay. So thanks for coming, and all the best. God willing,
Okay.
maybe 2 weeks from now. Okay. Bye.
All right.
All right. Thank you very much, sir.
Thank you too. Okay. Bye.
Bye.